Hello everyone, welcome to another exciting TBC Power Hour, and thank you for joining us. This is our first session, or the morning session of today. Today we're going to be talking about integrating multiple data types in TBC and discussing the rules around how TBC handles these situations. So my name is Boris Skopjak. I'm the product manager for TBC located in Westminster, Colorado. And today we have a special guest here with us, Troy. So let you introduce yourself in a few words.
Okay. Well, so I'm a software developer. I've been with TBC since the invention of the wheel. And so I've gotten to know quite a bit about TBC, not everything, but it's a lot of fun.
Excellent. Thanks, Troy. So please use the opportunity to type in any questions you have during the presentations into the chat window, and we will address them as we go. So the introduction to the computation engine is what we're going to start. Probably the term is not something that we publicize in our documentation. So the notion of computation engine is very internal to TBC and to the folks like Troy who work on the kind of the engines of the software. We're going to kind of talk a little bit more in detail about point derivation report and why is it so critical. And we will do an overview of computation rules in TBC, talk about the sideshot computations, and then differences between the computation engine, traverse adjustment, the network adjustment, and each of their roles in the workflow that you may be using. And we're going to try to summarize all of that towards the end and have next steps, and then we'll have a QA session. So we'll try to leave about 15-20 minutes towards the end for any questions that you might have. So again, please type them into the chat window at any point. Just what is a computation engine? So the computation engine is presented to you very commonly in the form of the red dot that you see in the bottom right of your TBC screen, as shown in the screenshot here. So every time you see a red dot, means something has changed and things need to be recomputed. Very often, if you have, for example, a chain of total stations, let's say you have a traverse of 30 or more total stations, if you change a prism constant or a backside on a second or third station in a chain, you know it has impact on 50th station down the road. So in that case, if you do change something, you will see a red dot prompting you to recompute. So as you know, in TBC there can be multiple influences on how the point is derived, and today we're going to be kind of focusing on how that derivation and how that final position of a point is derived. The goal of the computation engine ultimately is to provide initial positions for network adjustment, but it frequently does such a good job that a lot of people don't even go to that additional step or that extra mile to do the network adjustment and are content with the results that they get from the TBC computation engine itself.
Okay, so we're going to start with the point derivation report. The computation engine manifests its output in two different ways. Obviously, the positions of the points that it computes. But one of the other important ways that it manifests its output is in the point derivation report. So in this slide, we're looking at a screenshot of a point derivation report. This is very important because it tells you which of those multiple influences win over the other ones. And so if you look at the used to calculate column, you'll see that the top entry in that column is NEH. That stands for northing, elevation, and height. And so if you look to the left, you'll see there's an RTK vector from 50 to 84. This RTK vector was used to compute the northing, easting, and the height for this point 84. Down below that, you'll see an icon for a leveling observation from 507 to 84. This one was used to compute the elevation And the remaining entries that you see down below were not used to calculate the position of that point 84. I just want to kind of make a distinction between positions and coordinates here at this point. Do you see the office-entered grid coordinate that's second up from the bottom, that yellow and red circly thing? So we will try to use the word coordinate when we're referring to one of these things. This is an actual object inside of the program. And we will try to use the word position to indicate northing, easting elevation, lat long height, that sort of thing. So I know that that's, most people will tend to call the position actually the coordinate, but because we have these actual objects which we call coordinates, we're trying to make the distinction here.
Can you tell us, Troy, why is this office-entered grid, in this case, fourth in the order as in the resulting coordinates and not taken in consideration?
Yeah, so one of the rules which we will be talking about very soon here is quality. And do you see that green-looking icon that's by the office-entered coordinates positions? So this indicates that those positions are known with mapping quality. Yet the top line, the 50 to 84 RTK vector, is known with survey quality. That's what that little yellow-black icon thing says. And survey quality is better than mapping quality. So the quality is a strong rule in TBC, and that's why the office-entered grid coordinate did not have influence over the point, because it has lower quality. All right? All right, so the computation engine uses rules which are commonly called heuristics. Heuristics are rules that work most of the time, but they may have situations where they don't work so well. For example, we have the rule that when a traffic light turns red, you're supposed to stop. But if you're being chased by a T-Rex, I think that you would probably want to skip that rule and just blast on through the intersection. So heuristics are possibly going to fail in some situations, but in the general rule, they will work fine. So the first rule is position quality. And we just mentioned that with the coordinate that we saw there being mapping quality or lower. And this is the strongest rule. And so if you have two positions that are of different quality, then the position with the higher quality is the winner. And that one will influence the point, and the one with lower quality will not. If the position qualities are equal, then we go down to one of the next two rules. The number 2 and 3 rules are the secondary levels in the hierarchy. So the number 2 rule, the coordinate ranking, applies to those coordinate objects, the red and yellow things. And the number 3 rule applies to measurement methods. These are both similar kind of rules, but they deal with different kinds of entities. We will get into these more in just a minute. And then if all else is equal, if the position quality and the ranking and the measurement methods are all equal, the final and weakest rule of all is the chronology rule. And this chronology refers to the calculation order, not necessarily the order in which you did things in the field, but as long as you import the data more or less in the same order in which the data was collected, then the chronology rule will pretty closely mimic the data that the order in which things were done in the field. Okay?
So you'll start with the rule number 1, again, the position or the point, which you think in a resulting point, as Troy said, the final north and easting elevations and heights of the point. So the position quality can take multiple forms. So everything that you see here in the list from point number 2 to point number 8 is something that you can key in, or it is imported, or actually it's measured. It's a total station or GNSS observations, or it's a result of computation. Here what you see on top is the network adjusted coordinate. That's a label that is not visible in TBC, so it's not as transparent as these other ones. But if you have performed network adjustment, that type of coordinate is going to take precedence over these other 7. So you can see here order in these, how these positions are stacked in terms of quality. Also, you will notice an asterisk here next to the geoid quality, something that people very frequently kind of glance over in the project settings under coordinate systems under geoid. You have the ability to change the quality of the geoid, and this plays a role when you have especially a mix of GNSS and total station observations. So if you have total station observations only, or you have GNSS observations only, there's not even a need to use the geoid. Every time you have both in the same project, you have to use the geoid, because geoid links the two. So if you have total station, you will have northing, easting elevations, and then when you add geoid to it, you will get the height. Similarly, when you have GNSS observations, you will have lat, long, and height, and then applying the geoid gives you the elevation coordinate. So you have to make sure that if your observations are survey quality, that your geoid is of close of a quality and not remained as an unknown quality or mapping quality.
Well, you do want the geoid quality to be realistic. I mean, if it's not a good geoid, you don't want to be saying that it's survey quality. And if it's a bad geoid, you don't want to be, I mean, sorry, if it's a good geoid, you don't want to say it's an unknown quality. So it needs to be realistic. Okay, so we're going to talk about the basic computation model. This model is how most of the calculations are performed in TBC. When you repeat this model over and over again, then you can chain things together and get things like traverses and other kinds of network expansion. All right, so the basic model begins with a position for a station, some kind of an instrument that's able to measure things. And so in the left-hand side, you'll see the tripod sitting over a mapping quality point. So this is the beginning of the calculation. So knowing the instrument height, we can calculate where the instrument is actually located. Then we apply some sort of a delta vector in the form of, well, for total stations, it would be circle readings and slope distances, and for RTK vectors, it will be a delta XYZ values. So we then add that delta vector to the instrument's position. That gives us the target position. We then subtract off the target height, and that gives us the point on the ground. So this is what's called a mark calculation. We go from the ground mark of the instrument to the ground mark of the target. Now, it's important to understand that each delta observation has a quality of its own. So the point that the instrument is sitting over has a mapping, in this case, a mapping quality. All instrument-derived observations, like you see in green there, those have survey quality. And so what is the quality for the final ground mark that we're trying to compute? It will be the lesser of those two qualities. So mapping quality is less than survey quality. Therefore, the ground mark that we're computing has to be mapping quality. Now, let's take another instrument. So we have, in this case, a GNSS receiver. It's sitting over top of a control point. The delta vector that comes from that instrument is like the other one in survey quality. So what is the position of the ground mark that we compute from this calculation? Well, we have control quality, we have survey quality. Control quality is higher than survey quality. Therefore, the lowest is survey quality. So the ground mark that we compute from that calculation will be survey quality. So we have two ways of computing the position of that ground mark. We have the mapping quality and the survey quality positions. The lesser is mapping quality, therefore it loses. And so the final position of the point will be defined by the survey quality position computed from the right-hand side. We have a demo. Let's see. we have this point 50. By the way to get a point derivation report is just right-click on the point that you want to investigate and choose point derivation report. So we are now looking at the point derivation report for point 50. Do you see that there is an RTK vector from 1438 to 50? It has mapping or survey quality, and it was used to calculate the northing easting elevation and the height for this point. There's also this office entered coordinate. It has unknown quality, and because the office entered coordinate has a lesser quality, then it loses and the RTK vector wins. Well, now you might have noticed that this is a little bit odd, because if we close this and go back and look at the project, you'll see that point 50, which is down here, is actually the base station, and this 1438 point is one of the rover positions. And so we might ask ourselves, well, why did that position have such good quality? And so if we do a point derivation report on the 1438 point, we will see, oh my gosh, it has a survey quality coordinate assigned to it. And so what's happening here is normally the base station has the better quality coordinate, but in this case the rover has the better quality coordinate. And so this causes kind of a role reversal. Instead of the rover acting like the rover now acts like the base station. And so the information flows from the highest quality to the lowest quality, meaning that the position is calculated from the rover position. We start with the rover's coordinate. We calculate up to target height, backwards through the delta vector over to where the station is, and down through the instrument height to get the ground position of the base station. This is a technique called backing in your control. And so the information is flowing backwards in this situation. Now, if we go back to point 50 and we change the quality of this coordinate here, you see it's currently unknown. So if we change that to survey quality, now the base and the rover will both have survey quality coordinates. Let's see what that does to the point derivation report. You see now that the coordinate now wins. And so it's used to define the position of this point. And the RTK vector is not used to control the position of the point. This is the more normal situation. Then if we did a point derivation report on 1438, we would still see the same thing, that its coordinate is now winning. So what would happen if we were to, let's say, change it to enabled as check? And then we'll do a point derivation report on that guy. And so now you see that the position, the delta vector from the base station, is defining the position of the rover point, as you would normally do. But so anyway, this demonstrates two things. It demonstrates that the calculations can go both directions. It supports the workflow, the normal workflow, plus backing in your control. And then also, I don't know if you noticed this or not, but when we changed the base station coordinate to survey quality, then it won over the RTK vector. So this shows you that coordinates have a higher ranking or a higher influence than measurements do. Okay?
So just to add to that, backing into your control, a common question that we get from users that were very comfortable with the Trimble Geomatics Office, TGO, we get that question about reversing the flow out. So this is essentially the demonstration in the last 2 minutes showed you how you can essentially back into your control just by playing with the quality of the base and the rover position. So if this doesn't produce a tiebreaker, so let's say everything is survey quality, the second rule that we go down the chain that produces a tiebreaker is the coordinate ranking. So when we, again, coordinate here refers to that red and white globe object that you see next to your coordinate object in TBC. So the rule number one is that the global coordinate outranks grid coordinate, which outranks local coordinate. Let's say now everything is global or everything is local. So then the rule number two that produces a tiebreaker in that case is that the last added coordinate to the project outranks the first added. So the logic here is that you may have done some more due diligence later on in the course of the project. You found out the more accurate coordinate from your local cadastral office or from your previous projects, and then you have added these later on. So the last added trumps the first added if they're all global or all grid or all local.
Okay. All right. All right. So we're going to go to let's see, Shift Tab, Alt Tab. That's TBC. Okay. We're going to go to Demo 2. Where is Demo 2? Okay, so this project is very simple. It has just a .50 and it has an office-centered grid and an office-centered local and an office-centered global coordinate on it. And so these coordinates, if we display them, they all have survey quality. So how does the comp engine choose the position of .50? So let's do a point derivation report. And this will demonstrate the coordinate ranking. Do you notice that the global coordinate there is used to define the northing, easting, and the height of the point? Well, now, Boris just said that global coordinates have a higher ranking than grid coordinates. And so you would expect that. But look down here in the second line. You see that the grid coordinate is defining the elevation. So if the global is outranking the grid, why is the grid defining the elevation at this point? Well, the answer comes because the lat, long, and height that you get from the global coordinate cannot produce directly an elevation. So we have to use a geoid transformation to go from lat, long, height to the elevation. When we do so, we get one of those geoid quality things that Boris was telling you about earlier, the ones with the asterisks by them. And so what that does is it produces a slightly lower quality for the elevation that is calculated from the global. And because it has a slightly lower elevation, then the survey quality elevation that comes from the grid coordinate here wins over it. And that's why you see the elevation coming from the grid coordinate and not all from the global coordinate. So this little demonstration is showing you how the coordinates rank. This is the first rule that Boris was explaining to you. Okay, now we're going to go into this next file, Demo 3. Now, in this file, it looks very much the same. If we expand this .50, you will see that there is now this imported global coordinate. Now, the order was important here because the keyed-in office coordinates were done first, and then the global coordinate was imported afterwards. And so what we're trying to show here is that the order of things being added to the project makes a difference. So if we do a point derivation report on this guy, you'll see that this imported global coordinate that's at the top of the list, it was used to define the northing, easting, and the height. Once again, the grid coordinate defines the elevation, and then the office-centered global down here is not having any influence. So this is the rule 2, which is that the last one entered into the project is the winner when everything else is equal.
So just to add here, the most common practice people tend to use is just to delete other coordinates. Recommendation is that you leave all the coordinates in the project. They definitely don't hurt, and they can actually come in useful. If you have gone and changed any of these office center, global, or local as checked coordinates in the properties of those coordinates, you can see here in the point derivation, you can see the deltas on those coordinates. So they definitely don't hurt. So there's no reason to be deleting these from the project, as this is a really good way to detect any blunders. So if any of those coordinates is way off, this is a warning sign. So you can see here how the status of the office center global is now checked, and you can see what is the delta of that checked coordinate from the resulting northing, easting, and elevation.
Oh, it's probably worth to note here that check coordinates like this do not have an influence over your project unless there is no other way to compute the position of the point. If the check coordinate is the last resort, then it will be used to compute the position of the point. Okay. Okay, so measurement methods. Now, you noticed how that there were different ways of determining which coordinate would win over which other coordinate. So coordinates are different kinds of objects than measurements, but there's similar kinds of rules that apply to measurements that sort of mimic the rules that we have with the coordinates. So most surveyors are familiar with total station measurement methods. The most common, of course, is the direct measurement. But there's also some other kinds of measurement methods: angle offset, dual prism, distance offset, and the circular object. So these other kinds of measurement methods are more indirect in nature. There's a greater chance for error when measuring something with, let's say, distance offset, because the user, the rod man, has to get out his tape measure, and he has to measure from his current position to the object that's of interest. And so that additional measurement reduces the accuracy slightly, and therefore when you have a direct measurement compared with one of these indirect measurements, you would like the direct measurement to win over the indirect measurement method. And so that's what these measurement method rankings are all about. So we have a demonstration about that. Boris, could you bring up TBC? Thank you. So demo 4 shows that. There it is. His screen is a little small, so he needs to help me sometimes. All right, so what you're looking at here, this is a standard loop traverse, back sighting 5, and then it goes around this object here in the light green color. But at each one of the stationing points in the traverse, an observation was made to this point number 1 that's in the middle there. So let's do a point derivation report on this point number 1, and you'll see what I mean. All right, so one of the measurements to point 1 was a direct measurement. That's what the first one in the list is all about. Then second in the list, you'll see an angle offset measurement method. Third in the list is a distance offset, then a circular object measurement method, and then the last one is the dual prism measurement method. So the direct measurement method is generally more accurate, and so we have the heuristic that says that direct measurement should win over indirect measurements. So there's also rules that say which one of these indirect measurements should win over other indirect measurements. So that's what that table was trying to tell you there. So you see that in the point derivation report, this direct measurement was used to define the northing, easting, elevation, and height of this point, and the other ones were not used. If we were to then go to this measurement here, and we were to then, let's say, change it to enable this check, and then get another point derivation report, you'll see now that the direct measurement is used as a check shot, and so then the next level down is to use the angle offset measurement method. That's used to compute the horizontal position, and then the circular object measurement method was used to compute the elevation and height. So this is a demonstration of the measurement method hierarchy that you see there. Similar to the way the coordinate ranking works, this is like measurement ranking.
Okay, so reviewing the previous three rules. So let's say you have everything with survey quality, everything is global, they're all direct measurements, so we need a fourth tiebreaker. So the fourth tiebreaker is the chronology. So what chronology means is we kind of refer to it as waves of calculation. So TBC mimics the way how you would hand compute coordinates in the field. In this example, let's say you have positioned on the point A and you have taken a backside to point B, you've taken another foresight to point 1. At that point already you can determine the coordinate of point 1. But then you move the instrument to point B, you backside A, you take a foresight to point 2, you move the instrument to 2, you backside point B, and then you take a foresight to point 1. So that's a second way to compute the point 1. So when we refer to waves of calculation, we say that this is our first wave of calculation. So this is what we get. This is how we derive the position of point 1 in the wave 1, and then in the wave 2 we can arrive to the position of point 1 as well. So in the next few slides we're going to discuss how this chronology is handled and how you can decide whether you want to mix wave 1 or wave 2, as we explain a little bit more how the side shots are handled and how different types of observations are handled.
Okay, could you bring up TBC there? All right, so this demonstration, it has those waves in it. I hope they don't get the computer wet. This project is also very simple. The control point that you see in the upper left-hand corner is 99. So the instrument was first placed there. It backsighted this point 100, which is over here to the right. And then using that position and orientation, it was able to compute the position of this 100 EL point. So in wave 1, it was able to compute the position of 100 EL. And then also in wave 1, it was able to compute the position of this side shot 101 that you see down at the bottom. So in wave 2, what happened is the position for 100 EL was used to then compute the position of this 116 point that you see down on the right. And so it backsighted 99 and it foresighted 116. And then it took a side shot here to point 101. All of that took place in the second wave. In the third wave, we did the station setup for 116. We backsighted 100 EL and we foresighted 101. And so this was done first, this was done second, and this one was done third. And so the chronology rule says that this one has greater rank over this one, which has greater rank over this one. So let's look at the point derivation report for this 101 point. And you will see that the measurement from point 99 to 101 was used to compute the northing easting elevation and height. So what if we disable that one? So here's that observation that we were just looking at. This was the winner of the previous calculation. So if we disable that and we go back to the point derivation report, you will now see that the second one from 100 EL to 101 is now the winner. It's used to compute the position of the point. And so this demonstrates the chronology rule. All right, so the rules that we've talked about, the heuristics that we've talked about, have been sort of microscopic in nature. Whenever a position can be determined multiple ways, then those rules apply. And so the comp engine uses those rules to decide which of those positions will be the ones that control the final position of the point. But let's also now have a look at the big picture of how the computation engine works. So this simple flow chart that you see off to the right is our attempt to try to explain how that works. So all surveys begin with known positions. So these are typically like control coordinates. And so the first thing that the computation engine does is it looks for the coordinates that have the highest quality. So typically that would be control quality coordinates. At that point in time, it's currently ignoring the lower quality coordinates and focusing only on the control quality coordinates. So the second step is to compute the positions in order, and that means the order that you see off to the left. It first takes the positions of the coordinates and allows them to influence the point position. It then uses leveling observations, and of course they are only 1D, so it's only able to compute the elevation of the point. It then uses GNSS information and allows that to compute the position of points. And the last thing is total stations. There's actually more things like bundle adjustments and other stuff that goes on in there, but we wanted to just keep it simple here. So because the measurements are made in this particular order, and then if they all happen to have the same quality, then the chronology rule applies here as well. So for example, if we started with survey quality coordinates, we had survey quality leveling observations, survey quality GNSS measurements, and survey quality total station measurements, then you would see that coordinates would have a greater influence over leveling, leveling would have a greater influence over GNSS, and so on. Now, one of the things that probably would make your eyebrows raise a little bit here is, why do we have GNSS over total station? That seems a little bit backwards. You've spent a lot of money on that 1-second gun. Why is it losing to GNSS observations? Well, this is one of the heuristics that is probably the most difficult to understand. Typically, GNSS stuff is used to establish very large networks. And so then you densify your network using total station. And so you want the information to flow from the large network inward towards the densified position that you get from the total station. So this rule has been in place for over a decade, and we feel that it's the correct rule, even though it sounds backwards. Okay, so then the last step after it's computed everything that it possibly can compute from those high quality coordinates, it asks the question, are there any more coordinates? And if there are, then it goes back and it loads the next level of coordinates down in the ranking. So if it started with control coordinates, then the next time through this loop it would try to load the survey quality ones and compute everything that it could from the survey quality coordinates. And then it would load the mapping quality and compute everything it could from the mapping quality. And once again, the chronology rule is at work here, because the positions that are ultimately derived from the low quality coordinates come in last. And therefore, in the chronology of things, they have the lowest possible ranking due to the chronology rule.
Just one thing to add here on the topic of GNSS versus total station. Please don't confuse the computation engine with the network adjustment. So TBC doesn't use just one way to compute the position, which we will cover in the next few slides when we talk about how sideshots are handled. But the proper way to handle the weighting is through the network adjustment. So in the project setting, under default standard errors, TBC will know that you have a 1 second gun, and it will give that 1 second gun a much higher weight than the RTK in the process of network adjustment. So there's a step after the pure computation engine, what pure computation engine does in TBC, which is the network adjustment. And the network adjustment, same as in StarNet, Move3, or any other adjustment software, will handle the weighting in much more sophisticated way. And in that case, you will see that the total station takes precedence over the GNSS. If you have, for example, a mix of VRS and a mix of 1 or 3 second instrument, total station instrument, you will see that that total station instrument does take the higher weighting. So don't be alarmed by that. So that was actually a good intro to the next topic, which is the sideshot computation. So in that example, when Troy said the point 101, the weight was derived from 3 direct measurements computed in the wave 1, 2, and 3. There is actually a way that computation engine can handle and actually weight appropriately who gets the position of that point 101. Probably one of the most critical settings in TBC is this one here. So please take a note of this setting. Under the project settings, under computations, you will see a method for sideshot computations. There's multiple methods here, and the default one is the single observation. So in that example here on the right, where you have the wave 1 and wave 2 coming to the point 1, with the default method of the single observation, the wave 1 wins over the position of point 1. If we have used a weighted mean of all observations or weighted mean of all like observations, the wave 2 would be taken in consideration as well, and the weighting would be done based on the distance or the length of the vector. So the all observation just means if you have a mix of GNSS, RTK, and level, that will do the weighted mean of all. If you have total station or GNSS only, then you can decide to use weighted mean of all like observations. That's the difference there. So we recommend that you use single observations if you're following on with the network adjustment in TBC. If you are not running through a network adjustment and you're most of the time satisfied with the results of the computation engine, then we would recommend that you use the weighted mean of all observations. I very often use that setting myself, but in the next example we can show you how that can be very dangerous.
Mm-hmm. Okay, well, let's go to the demo 6 here. So you may recognize this is basically the same project all over again. Let's go to those project settings that Boris was talking about. Computation, sideshot computations here. So the default is single observation. But let's go with, just for the grins and giggles, let's go with the mean of all of the observations, show you what that does. So if we go to point 101 and we do a report on it, you notice that there's now a fourth item in the report, which is this simple mean object. And so this position, the position from the simple mean was used to define the position of the point. And then these other observations that you see down below there, they contributed to the simple mean. And you can see the residuals between the simple mean and the position as computed from these different observations. So there's not a lot of error in this project, but if we zoom into this point, we're going to, the reason for zooming in is we're going to explode this point and show you what happens now. So one of the problems with that project setting is that it's project-wide, and so all of your side shots would be handled in this manner. So what if you don't want that to happen? What if you want to pick and choose which stations will be computed with the mean and which ones will not be computed with the mean? Well, the answer is that you can use the explode points command, and the explode points command would normally explode these 3 observations to 1 point into 3 observations to 3 different points. Well, when you do that, one of the things that you may want to do when you explode the point is to create an average point. So we're going to have this checkbox here checked to create an average point. So when we do this, you'll see that there are now 3 different points, the 101x, the 3 101x points, and then the 101 point, which is the mean of those things. This explode point command is very handy in terms of looking for outliers. When you have multiple ways of determining the position of the point, you have redundancy, and that redundancy is very valuable to a surveyor. It allows you to check for outliers much better. So you can see that the scale is like only 1 centimeter per division here. So we're only looking at about 3 centimeters different between these 3 different measurements. And so there's reasonably close agreement with these 3, and so I would probably say there's no outlier. So what I could do is I could just undo, and then that would allow them to merge back into a single point. Then I wouldn't have this 101 computed that way. So if I did an undo, and then it would come back like that. So one of the cool things about this is that you can explode the points, remove outliers, and then you could use the merge points command to merge them back into a single point again, where you've already done your outlier detection. Or actually, perhaps what you would want to do is disable the outlier observation. Okay.
So the command you see here, the explode points and merge points and average points are actually kind of doing the opposite. So the exploding kind of allows you, if you have taken 10 side shots on the same point, as Troy was saying, you can see how those side shots fall within each other. Are they in agreement or not? You can decide to disable the 2 out of 10, for example, and you can then use the merge or average points command to get them back. Those 8 that you like, you can get those merged back together. So the merge is going to do the weighted, and the average is going to do the simple mean. So that's the difference between the merging and averaging. So same as in that project setting, the weighted mean and the simple mean are options, so the merge and average points are kind of following the same paradigm there.
Well, the merge point follows the project settings. So whatever your project settings tell the merge to do.
In that case, if you have used the weighted, if you use the merge points and the project settings for the side shot computation is the weighted mean of all observations, in that point derivation report you will see an object called weighted mean. And in that example Troy showed, it said simple mean. So this is an example here is a graphic where it shows where you don't want to have the weighted mean as your default method. So as I said, I personally choose the weighted mean, but it's very dangerous. You can get burned really easily. So in the scenario where you have a position here or station and this point, and you're shooting to this point with a question mark, and then you're moving in the traverse direction here as showed in these. So the numbers here represent waves of calculation. So as you're moving in these waves of calculation, you arrive to this point 8, and then you can see the same, you make a measurement from the same to the same point with a question mark. In the case where you have chose weighted mean for the side shot computations, that observation here, the shorter one, is actually going to have much more impact on the point with the question mark because the distance is shorter. So the weighting is a reciprocal of the distance. So the bigger the distance, the less the weight it has. So in that case, this wave 1 would have less weight and less impact on the point with the question mark. And that's something you don't want because as you're kind of moving here in this direction, you're accumulating error. So by the time you arrive to this point around here, you have a lot of error in your measurement already, which translates to that measurement here, and you will kind of carry over that error to the point with the question mark. So this is an example where the weighted mean should not be chosen as the default method. But and it also, this example serves another purpose to show that the value of traverse adjustment or network adjustment. So the NWA stands for network adjustment here. So in case you're doing a traverse adjustment and you're balancing all the errors here between your angles and distances, in that case weighted mean is a good method to run. So if you have run a traverse adjustment, that means you have lost most of your errors when you arrive at this point. In that case, it's okay to do the weighted mean. But the most sophisticated way to handle this weighting is the network adjustment. So we strongly recommend that you use the network adjustment in TBC, as it will kind of do a much better way in balancing these errors throughout the entire project, and it will choose the best position for the point question mark. It doesn't hurt if you're planning to run a network adjustment. It doesn't hurt to have a weighted mean as a setting. At that point, it doesn't matter whether you use a single observations or a weighted mean. the network adjustment will do its job and choose the best way to compute the position of the point. If you're not planning to run a network adjustment, just think of this picture every time you run into TBC. So if you have a very simple case scenario where you have another direct measurement here to the point with a question mark and one direct measurement from this left-hand side to the point with a question mark, then weighted mean is okay. But if you have a situation like this where you're kind of traversing a lot and it takes you a while to get back to the point in case, then you probably want to stick with a single observation, which is why we have chose it as the default method, assuming that you would run a network adjustment in TBC.
So I think most surveyors would probably do a traverse adjustment if they were not doing a network adjustment, and so in that situation it'd be okay.
Yep. Cool. This kind of takes us towards the end. We want to make sure we have time for questions and answers. So just to summarize, the role of the computation engine is to provide initial positions for network adjustment dominantly. Just to recap on the rules, the position quality takes precedence over the coordinate ranking, which takes precedence over the measurement method, and then the final tiebreaker is the chronology. So if all the three above are the same, then the chronology takes precedence. And just on the recap on the last few slides, the single observations is preferred if you're not going to run the network adjustment. Just for the next steps, we know this was an advanced session for TBC, and I hope those that are new to TBC didn't get disappointed. I'm sure this session is going to serve you later on as you get more comfortable with the software. You can always watch the recording, which is going to be available on the Power Hour website. If you have not used TBC so far, you can get a license, demo license from one of our Trimble distributors, and there's tutorials you can start playing with and watch the YouTube videos. Just to announce, the next Power Hour is on April 27. We're going to focus more on working with optical data. We're going to go through the process of queuing total station data using optical spreadsheets, doing things like changing station setups in the office, look at the editor, how the MTAs are handled, and look at traverse adjustment at that time in a little bit more detail. With that, I want to open it to questions and answers. So first question came in from Stacy. Can you explain the merge points dialog box that appears when duplicate point numbers exist in different files being imported into TBC?
Okay, so the import process starts with sort of a part of the project that's out all by itself. So the imported file goes into this project where it's not connected yet to your main project. We then try to compute that project so that we can get positions. Now the reason for doing that is so that when we have duplicate points that is points with the same ID, that we can make a determination whether they are supposed to be the same point or not. And so after we've computed the positions, we look at the points with the same point ID, and if they have positions which are within a certain tolerance of each other, then they will be checked in that dialog. The positions that are too far apart will be unchecked. So you have the option of overriding that. You can uncheck and check things as you please, but the initial state of the checkbox is based on position. There's a project setting that controls all of that. Do you want to go to that project setting, show that? So if you go to the project settings under computations, point tolerances, this setting right here controls that. So the default is point tolerance times 3. So for example, if they were survey quality points, then we would take the point tolerances of 20 millimeters and 50 millimeters up there, multiply by 3, and then any points that are within that would be checked by default, and the others would be unchecked. So then there's also the possibility for a custom tolerance if you want to put in your own tolerance there too.
Stacey, I hope that answers your question. There are a couple of questions about the jury. So Travis and Jaren were commenting the the geoids do come from NGS in most of the cases. So the question was, how would you determine which geoid quality to use?
Right. So the coordinate system database, I think, has some qualities built into it. But ultimately, since the responsibility is yours, there are also probably websites that contain the quality information, or at least how good the geoid is. But it's not represented in terms of the survey mapping unknown quality that TBC uses. So it would be up to you using one of these websites to determine which quality applies. I would say it's probably safe to assume that most geoids are going to be survey quality.
Yep. Yeah, especially coming from NGS, I think typically are survey quality. But again, as Troy indicated, we give you the option, as in some of the areas you may have a better geoid approximation than in other areas. In that case, or if you're running level runs and things like that, you have the flexibility of playing with that geoid quality a little bit more. So therefore, ultimately, it is your decision.
So just to recap, geoid quality is only important when you have a mixture of GNSS and total station data. And it's usually also only important when you have something other than survey and control quality stuff. So if you have mapping quality things, then that's when it starts to come into play more.
Stacy had a question saying, when adding a control quality coordinate for the base point of RTK vectors, sometimes the elevations do not recompute along with the horizontals. The only way I can get TBC to adjust the elevation is to delete the global file for the base point. Why does this happen, and is it acceptable to delete the global file?
By global file, are we talking about the global coordinate?
I would assume that to be correct.
Oh. This is a strange question.
So Stacy, this is a little bit longer, might be specific. Both horizontal and the elevation should recompute. Might be related again to the presence of geoid in your project or not.
I wonder if she's using shift grids, because with the shift grid or the type of system, then it's possible that there will not be a shift grid at both ends of the vector. When that happens, then we have problems with things computing, and we have to use a fallback technique.
Okay, so Stacy, if that didn't answer your question, please feel free to email us with your data and the example in the case. Adam is asking, if we have two optical observations from a mapping quality point to 2 points that are survey quality, will a survey quality position for the mapping quality point be calculated?
So I would say no. If I understand this right, I'd say no, because if you start with positions that are mapping quality, then the best that you can do for the rover point or the target point would be mapping quality. And so if the target point is already survey quality, I assume that must be derived from either a coordinate or from an observation. Whatever makes it into a survey quality point will win over the mapping quality observations from those two optical observations.
Stephen is asking, could we describe the difference between the global and local and when to use which? This is probably a big topic that deserves another power hour on its own, the global, local, and grid.
Right.
So it's going to be a very lengthy answer to that question. But Stephen, I would recommend, and for everybody else interested in that global, local, grid, we did a session in October when we talked about similar topic. We discussed the global, local, a little bit more detail, and local sites and site calibration. So please refer to that session. And we can, in your comments to this session, if you want to kind of do another deep dive on that topic of global versus local, we can do one of the following power hours on that.
I could take a quick stab at this if you want me to try.
Sure.
All right, so the main reason for having local coordinates at all is because of the ellipsoid. With global coordinate systems, you have a global type of an ellipsoid, and so The ellipsoid is where the reduction calculations are made. Whenever you are computing total station observations, they are reduced to the ellipsoid, and this is mainly to get the change in elevation. So the curvature of the ellipsoid and the direction of curvature, all of those things play into the role. So if you are trying to mix GNSS and total station data, then the ellipsoid is important because the elevation calculations depend on it. Well, what happens is with global ellipsoids, they are pretty good as a global thing, but they're not very good locally. And as a result, you'll get better results with your total station reductions if you have an ellipsoid which better approximates the curvature of the Earth in your locale. I hope that helps.
So I hope that helps again, Stephen. And again, if there's interest in this topic, we can repeat that session from October with a little bit more depth. Blake is asking, is there any kind of warning that a check is? You said that the check shot is the ultimate result.
Oh yes, no, there is no warning that I'm aware of. So if a check shot is used to compute the point, then the only way to find out about it is to look through the point derivation report.
Yeah. Is the hierarchy used in TBC for computation the same or similar in access to compute values shown in the field controller?
Hard question. I'm not sure about that one. I know that we've taken a lot of pains to try to make sure that TBC and Trimble Access compute things the same, except that there are a few minor differences. So I would have to say probably yes. Probably the hierarchy is basically the same.
Yeah, the common question comes with the confidence level display. I think was that in here. There's very frequently we get a question why Access and TBC are showing different precisions on points, and that is why that is because Access is reporting confidence level as 1 sigma. And TBC is doing it at 2 sigma at 95% because we feel like the office software should be a little bit more strict than the field software when throwing out warnings and flags for the points.
Mm-hmm. Plus the assumptions about the default standard errors may be a little bit different too.
Yeah. So Jerry had questions about if there's one observation used or only one measurement of point being used. And I think we've answered that. So you can have multiple observations used in computing a point if you choose the weighted mean or a simple mean of sideshot observations, and then the network adjustment will definitely take everything in consideration. Dustin is asking chronology order. If you change computations from single measurements to weighted mean, does this affect chronology order or not?
So the chronology doesn't apply for side shots that are computed from a mean like that. So the chronology mostly applies to the single observation mode.
Ryan is asked, clarify, does the simple mean bypass all of the other consideration, for example, GNSS versus total station?
Essentially, yes. So the chronology rule, well, there's still the stronger rules, which are the quality. So when we mean things together, if I recall properly, we don't mean things of different qualities. We choose the highest quality and just mean the things of the same quality.
Yeah. There are some comments about hierarchy and the computation engine. So this was new to a lot of people on the call. So I hope this demonstrates and serves as a purpose that TBC does have the geometric roots, and we are the survey software. So I hope you kind of get a better confidence now when you're using TBC, knowing a little bit better on how it works intrinsically. There were a couple of more questions. I'll just kind of quickly go through them as we are a little bit over time. can we merge 2 or more projects into one project? That's actually, I'll give you a kind of a sneak preview as a reward for staying 5 minutes over. I'm using TBC version 370 here, which we are releasing in about 2 weeks. And everything we showed here is already in release version. So there's not a single new thing that in Troy's demonstration, there was nothing new. There's a new command here, merge survey projects, that Fahmi answered your question. So with TBC 370, you will have ability to merge survey data, edited survey data from one TBC project to another. So keep that as a sneak preview, and you can brag to your colleagues that didn't attend. I think with that, as again, we're running a little bit over time. We have another session in the afternoon. We'll try to answer the questions that we have not answered in the afternoon session. If you want to attend that one as well, you're more than welcome to. If you think of any other questions throughout the day, that's another opportunity to ask more questions there. And with that, I want to thank you, Troy, for making this presentation very worthwhile.
My pleasure.
And thank you all for attending, and I hope you're enjoying these Power Hour sessions, and let us know what we can be doing better or what topics are of interest, and we will try to fit those in. Thank you again, and have a great day, everybody, and have fun using TBC.